Hey there, and welcome. Have you ever stopped to think about all the, stuff that's around us? Everything you see, touch, even smell, it's all made of matter. But how in the world do we make sense of it all? Okay, let's dive right in and actually build a kind of map to classify everything in the universe. It really all starts with a super simple question. Just look around you for a second. You've probably got some wood, maybe some plastic, a glass of water, the air you're breathing. It's all matter, but it's all obviously different. So where do we even begin to sort it all out? Well, let's start with a couple of examples you've definitely seen before. So on the left, you've got salt stirred into water. It just kind of disappears, right? You're left with this clear liquid. But on the right, we've got sand in water. You can totally see every little grain of sand just swirling around in there. Now, both of these are mixtures, but they give us a massive clue about the first big way we can start classifying all matter. And that clue leads us right here to the first big split. Every single thing in the universe is either a mixture or a pure substance. That's it. This is our starting point, the first major fork in the road to understanding what everything is made of. Think of this flowchart as our roadmap. It all starts with one fundamental question you can ask about any substance. Can you physically separate it into different parts? If the answer is yes, we go down one path. If it's no, we go down another. So let's follow that yes path first. So, if you can separate something using physical means, like running it through a filter, or just letting it settle, or maybe boiling off the water, then you've got what we call a mixture. And the key phrase here is physically combined. The salt is still salt, the water is still water. They haven't become a new thing. They're really just hanging out together. And it turns out mixtures themselves come in two main flavors. That salt water from before, that's a homogeneous mixture, which we also call a solution. It looks exactly the same all the way through. But the sand and water, that's a heterogeneous mixture. You can literally see the different parts. So really, it just comes down to a simple question: can you see the ingredients or not? All right, let's rewind and go back to our map. What happens if the answer to can it be physically separated is a big no? Well, then you've got yourself a pure substance. Think about pure sugar or the pure oxygen in a diver's tank. You can't filter it or strain it to get different things out of it because it's only made of one thing. But hold on, our journey is not over yet. For these pure substances, there's another really important question we have to ask. We're about to get down to the truly fundamental building blocks of, everything. So the next question on our map is this: can it be broken down by chemical means? If the answer is no, you've hit bedrock, you've got an element. It's the absolute simplest that substance can be. But if you can break it down with a chemical reaction, then what you have is a compound. Let's make this crystal clear with two examples. First, think about an element, like the pure oxygen inside this tank. That's it. It's as simple as that substance gets. Now look at this compound, this red powder called mercury oxide. If you heat it up, a chemical reaction happens, and you can actually break it apart into two totally separate elements, the liquid metal mercury and the gas oxygen. Okay, so let's try a little thought experiment. We've all been taught that water is H2O. That formula right there tells us it's a compound made of hydrogen and oxygen. But, talk is cheap. How could we actually prove it? How could we physically rip water molecules apart and see those two elements with our own eyes? Well, the answer is electricity. This cool-looking device does something called electrolysis. By running an electric current through the water, you're pumping in enough energy to actually break the super strong chemical bonds that hold the hydrogen and oxygen atoms together. And what's the result? The device collects two different gases in those tubes. And boom, it's successfully separated and captured the hydrogen and the oxygen. Proof. So up until now, we've been talking about stuff we can see and handle in a lab. But to really, truly get the difference between elements and compounds, we need to shrink ourselves down. Way down, and see the world from the perspective of an atom. This chart basically shows us the whole game. You can think of these individual atoms, hydrogen, oxygen, and so on, as being like different colored Lego bricks. They're the basic pieces. Now, let's see what happens when we start snapping them together. So what does a pure element look like at this tiny scale? Well, sometimes it's just a bunch of single, unattached atoms floating around, but other times, atoms of the same element like to buddy up. A perfect example is the oxygen we're all breathing right now. It isn't single O atoms. Nope. It's pairs of them, bonded together into what we call O2 molecules.
And here's what one of those little guys looks like up close. It's just two identical oxygen atoms chemically stuck together. And because they are identical, we still call this whole thing a pure element, not a compound. That's a really important point.
So what makes a compound's molecule different? It all comes down to a single word: variety. When atoms from two or more different elements bond together, that's when you form a molecule of a compound. And that's when you get a totally brand new substance. A perfect example of a compound is this molecule of methane. It's the main ingredient in natural gas. You can see it's one carbon atom chemically bonded to 4 hydrogen atoms. Because we've got different elements, carbon and hydrogen, joined together, this is the textbook definition of a compound. Now, I know this can all feel a little abstract, like something that only matters in a chemistry lab, but understanding compounds is so much more than that. Turns out humans have been master chemists for thousands of years, and this next example is, well, it's one of my all-time favorites. This is the chemical formula for a pigment called Egyptian blue, and it's a compound. You can think of this formula like a recipe. It's telling us exactly which elements the ancient Egyptians had to combine and in exactly what amounts to create this absolutely stunning, vibrant blue color. They were literally creating brand new matter from scratch. And just look at the result of their chemistry. On the left, that's the compound, the pigment itself. And on the right, you can see it used in their art that has survived for millennia. This beautiful, incredibly durable color only exists because people figured out how to combine different elements to make a completely new compound. Just let that sink in for a moment. The very first color that humans created, that wasn't just crushed up from a rock or a plant, was a man-made chemical compound. I mean, that's a monumental leap in human history, and it's all based on the same exact principles we just mapped out. It's chemistry becoming art. So, take another look at the world around you. The plastic in your chair, the sugar in your kitchen, the paint on the walls. They aren't just stuff. They are carefully designed and constructed compounds. Now that you have the map, what are you going to see differently?